If contention is low in our system, it would be natural to try to remove the burdens of additional mechanisms, such as locking and unlocking, that are meant to reduce problems of contention while doing concurrency control. Validation-based concurrency control is based on this idea. Assuming that most transactions do not conflict, we allow transactions to execute and just check at the very end to make sure that everything was indeed okay. In this method, transactions proceed in 3 phases: read, validation, and write. In the read phase, a transaction executes, reads data from database, and writes the data to a private workspace. When the transaction is complete and it wants to commit, the database management system now checks whether there has been a conflict with any other transaction that has been running concurrently. If there has been a conflict, the transaction will abort, the private workspace will be deleted, and the transaction will be restarted. This phase is called validation phase. If there are no conflicts, the transaction will proceed and the changes will be written to the database and commit. To be able to validate, there is a need for a mechanism for tracking accesses to the objects. Validation-based protocols use timestamps for this reason. But the way the timestamps are used in these validation-based protocols is different from how we use them in timestamp-based protocols. Each transaction Ti receives a timestamp that we will denote with Ts of Ti at the beginning of its validation phase. This timestamp is used to validate the equivalence of the transaction's effect to some serial schedule. So, for every pair of transactions Ti and Tj, one of the following 3 conditions must hold. Either Ti completes all of its 3 phases before Tj begins, or Ti completes before Tj starts write phase, and Ti does not write any database object read by Tj, or Ti completes its read phase before Tj completes its read phase, and Ti does not write any database object read or written by Tj. So basically, these rules provide different levels of overlapping, ensuring that still the changes made by one transaction is not visible to the other. The first one ensures there is no overlapping and the schedules are running as serial transactions, one following the other. The second rule ensures one transaction finishes before changes made by the other. And the third rule, the most permissive one, ensures overlapping of sections of the transactions performing reads and writes that are safe. For example, we have transactions T1 and T2. They both enter the read phase without doing any additional work and any overhead. They transfer the objects to their temporary workspaces as they proceed. When we reach the validation phase, the list of objects read and written by each transaction is checked. During the validation and writing phase, no other transaction commits. So, T1, earlier in time, is at the validation point now. Its validation passes the conditions 2 and 3, as it has not written any object that is going to be read by another transaction, and the read list does not show any conflict. So it is okay to commit, and it enters the write phase. It does not have a write. Therefore, no transfer of temporary workspace objects is necessary. So Ti is now finished. When T2 validates, there is no concurrent transaction violating conditions because T1 has finished its read phase before T2 is starting its write phase. Therefore, T2 can now commit, and the write phase of T2 can now proceed without conflicts. We can use the synchronization methods such as critical section synchronization to ensure at most one transaction is at its validation at any given time. Validation-based concurrency control is also known as optimistic concurrency control. This is because it assumes most transactions will proceed without conflict, and it does not do preventive actions ahead of time about it. It proceeds with transactions and performs validation as a last step to ensure conflict-free commits. This way, it removes the overhead of locking or unlocking or ensuring timestamps at every read and write. Taking the optimistic approach, it adds a considerably lower overhead, which involves the overhead of recording read lists, checking for conflicts, and ensuring the written objects transfer from the private workspace to the database at the write. This way, it has the possibility of higher performance compared to other schemes, especially if the validation is implemented effectively and the system has low contention, so that our optimistic assumption is helpful. Using the 3 validation conditions we discussed, the performance of this scheme could still be low, as the scheme is overly conservative. Using these rules can actually cause unnecessary aborts and restarts. The main problem here is that the earlier transaction is not allowed to write. However, if a transaction can write all of its objects before they're required by the later transaction, this could still be handled without any problem, right? So, what do? We have a list of objects written by earlier of Ti and Tj. But when we are validating, we do not have a way of comparing the time they were written so that we know if changes by Ti are actually read by Tj or not. The solution to this is using a mechanism similar to locking, but more lightweight. At the validation time of transaction Ti, we check whether any of the items written by it will be read by any transaction Tj. If that is the case, well, Tj needs to abort. It is either done right away, in which case we have a kill policy, or it will abort when it is going to be validated, which we call it die policy. To do this, we use a hash table with entries including transaction ID, data object ID, and modified flag. Modified flag is false at the beginning, showing the object is not modified. The data object ID is used for hashing. During read, a temporary lock is associated with the hash bucket of the entry, lasting for the copy time from database to the temporary workspace. If we implement the die policy during validation, all buckets associated with objects of the transaction in validation are locked. If any of the access entries are set to true, there is a conflict and the process will abort. If we implement kill policy after validation completed and the current transaction is to commit, all buckets associated with objects of the transaction in validation are locked, and all of the transactions with the access entries with modified flag will abort and restart. The kill policy is more effective than the die policy in reducing the waste of extra processing before abort.